Alien technology. How can we imagine it? In our last episode, we saw how galactic empires likely emerged billions of years ago, then settled into a long Cold War balance. If we believe they are still here, the next step is to ask, what would their technology look like, and what clues could it give us about our relationship to them? It's one of the hardest things to imagine, but also one of the most fun. In this video, we'll take the same rule that drives our own progress, apply it to civilizations thousands or even millions of years ahead, and what you'll see is shocking. The simple math shows their technology gives them abilities that defy common sense. Setting the curve for alien technology. How can we predict the advance of alien technology? Right now, our computers, sensors, and networks are improving at a steady pace, roughly doubling every 2 years. This is called Moore's Law. But is that pace realistic over the long run? As technology improves, there may be limits, bottlenecks, or plateaus that slow things down. To stay conservative, we'll use a gentler curve, one that doubles every 10 years instead of every 2. On the next slide, we'll see what it means for civilizations just a little older than ours. When 1,000 years changes everything. Here's what happens when we apply a 10-year doubling curve. Even a head start of just 1,000 years makes a civilization about 1,000,000,000,000,000,000,000 times more advanced. A gap we can barely imagine. Add more time and the numbers grow beyond anything that makes sense. But these estimates are more than just numbers. They give us a real-world ratio we can apply to our own technology, a baseline for picturing what their capabilities might feel like to us. And that's where we're headed next. Why we wouldn't understand a hello. Imagine that an alien said hello with a single burst of information in 1 second. Could we understand it? To get a sense of scale, think of this analogy. For every 1 letter of data we could transmit or process in a second, an A for example, they could handle about 1 trillion books in that same second. They are speaking in a higher dimensional language we cannot begin to understand. To them, we are moving in slow motion. They can have trillion book conversations in the same time it takes us to process a single alphabet letter. When space becomes the machine. When we think of control, we imagine levers, wires, or beams of energy. But what if an advanced civilization doesn't need any of that? In our labs, we work with things tens of nanometers across, molecules, proteins, even transistors. Now imagine a civilization working 30 orders of magnitude smaller, beyond anything physics can currently describe. At that scale, they wouldn't just touch particles, they'd be operating on the ticks of time itself, what some theorists call chronons. If space is a network, it would also be near that scale. By nudging the tiniest fluctuations of space and time, testing countless possibilities at once, think of it as the ultimate multitasking, they could bias reality toward the states they want. No wires, no beams, just the fabric of time and space itself, carrying their influence into our machines and into our minds. If gravity reaches that deep, so can they. When science becomes magic. The science already tells us aliens are real. That was parts 1 through 3. And in part 4, the science says they are at least 30 orders of magnitude beyond us. So unless we want to defy the weight of the evidence, we have to accept that they are real. And they are powerful. What we don't know is whether there's a limit. Maybe reality itself only has so much resolution, and they're already at the edge of it. Or maybe reality goes far deeper, but no technology can reach that far. Either way, our model predicts that even 1,000 years ahead, they would already be masters of reality as far as we can imagine it. To us, it would look like magic, beyond any natural explanation. So the question now isn't if they exist, the question is, when can we prove it? In part 5, we'll take on that challenge, calculating when we might finally detect them.